So based on the success of the reduced order model of SEI layer growth, we looked at some other mechanisms to model. And in particular, any kind of mechanism that involves some kind of a tuffle relationship is probably going to work reasonably well with the approach that we took. So one example is a paper by Darling and Newman, which might be the first paper that tried to propose a model of an aging mechanism. And they looked at a film on a positive electrode particle as opposed to a negative electrode particle. That would probably work well on that, but we haven't actually looked at that. One thing we did look at, though, was a different kind of aging mechanism that does not use a Toffel equation. It's based on a paper by Aurora and company, and instead it uses a modified Butler-Volmer relationship to describe the rate of the chemical reaction. In this section, we'll kind of quickly talk about the full order model, and we'll look at some results in the next section of a reduced order model of lithium deposition on overcharge, or otherwise known as lithium plating. This reduced order model is okay. It's certainly nowhere near as good as the SEI layer reduced order model, especially for prolonged charging events. And because of that, it's probably better suited for predicting degradation in a hybrid electric vehicle kind of scenario with random charging events instead of long, drawn-out charging periods. We are working on another method right now. We have some preliminary results that look quite a bit better, but at this point we aren't ready to share that method publicly. But we do think that we can make a reduced order model of this lithium deposition that works well inside of a control environment. When we look at the table of degradation mechanisms and what is the most frequent cause of cell death, lithium plating does not end up on that list, because lithium plating is kind of a severe thing. And if we keep a cell within the designed voltage limits, we will almost certainly not cause lithium plating. But we need to have a model of it inside some kind of an optimized control scheme, because the model doesn't know necessarily what cell voltages to use. It needs to know instead how to avoid degradation. And lithium plating can be severe if we aren't very careful. This is especially true at cold temperatures, when the terminal voltages are poor indicators of the internal cell potentials, and plating can still happen even at warm temperatures, and when it does, there's immediate and severe capacity loss. So there is, from a controls perspective, a lot of incentive for a good model of lithium plating, just for the very purpose of avoiding lithium plating by computing controls that do so. What happens, we have a negative electrode particle, and we have lithium that is trying to get into that negative electrode particle while we are charging, and the surface layer fills up, is at least part of what is happening there. And it's hard to get more lithium into this particle, but if we're forcing charge by applying a very large external voltage or a current source, we're forcing charge somehow, we have an Li plus in the electrolyte, and we can bring an E minus from outside the cell, and we can bring them together and plate metallic lithium on the surface of the particle, so that the lithium can't get in fast enough to intercalate, which is what we would like to happen. Instead, we plate metallic lithium on the surface. And this lithium can combine with electrolyte material to form other compounds like lithium oxide and lithium fluoride and lithium carbonate and polyolefins, things like that. The main point is that once lithium has plated, we don't get it back. We might get a little bit back, but at least in this model, we don't get lithium back anymore. And so our capacity goes down. And when lithium metal combines with other things to make these kind of products, we form a film on the surface, just like an SEI film, but a different mechanism that caused it to grow. So I lose capacity and I gain resistance because of this lithium plating mechanism as well. So this phenomenon, lithium plating, is an unintended side reaction. It can lead to severe capacity loss, electrolyte degradation as it combines to make these kind of things, and a possible safety hazard, especially if we start forming dendrites that short-circuit the cell and cause dramatic heating of this cell. Aurora and company in 1999 published a paper that proposed a physics-based model of lithium deposition on overcharge. And our goal is to create a high-fidelity reduced-order model of this PDE degradation model. So we are going to adopt the same assumptions as Aurora and colleagues did in their paper, and their assumptions were as follows. The main side reaction is that I've got lithium ion from the electrolyte plus an electron at the surface of a particle combined to form lithium solid, metallic lithium. And this happens when the overpotential of a side reaction is 0 volts versus the Li-Li plus reaction, which is by definition the potential at which lithium and lithium plus are in equilibrium with each other. The lithium metal is expected to form first near the separator boundary where the surface overpotential is the greatest, and it's going to form later near the current collector. Assumption 2 is that the lithium metal that's deposited reacts quickly with the solvent or the salt and makes these other products. So in a secondary reaction, we make these products, and a film forms, and it protects the solid lithium from reacting further with the electrolyte. We can still dissolve the lithium during discharge, but once lithium is consumed in one of these insoluble products, it's permanently lost. The products, we don't know what they are. We're not going to say what they are. We're just going to average them out. So they have averaged mass and density constants, just like we did with the SEI film. And we make this resistive film on the surface of the particle. And we consider only the overcharge reaction in the model and lithium deposition on overcharge. In this model, we do not consider SEI film growth or any other degradation mechanism either. The model that Aurora presents is tightly coupled in with a Newman-style porous electrode model, a pseudo 2D kind of model. And he changes the normal intercalation equation a little bit. And so here's the normal intercalation equation. He writes it with an I naught instead of a J naught, but that's okay. And so we have the Butler-Volmer two exponentials, just like we would expect. The main difference is that in this equation we have this R film constant, which we've seen other places before, but it wasn't in the original Newman-style model that we considered last semester. So there's nothing really terribly new in the Butler-Volmer equation for the normal intercalation reaction. But then he defines a side reaction flux for the overcharging reaction, which is the rate of irreversible lithium loss due to lithium plating. And the side reaction, you'll notice here, is also sort of a Butler-Volmer equation. Remember, the SEI model was a Toffel equation. This is Butler-Volmer, which means that it's semi-reversible up to a point. So we have the one term that dominates, this term here that dominates, but there is some reversibility. However, we always take the minimum of the Butler-Volmer result and 0 to mean that the side reaction current or flux is never positive. It's always non-positive or negative. And there's a side reaction overpotential that drives this, and it's defined to be phi s minus phi e minus a reference potential minus FR film times J, so kind of similar to what we saw for the SEI model, except this here is 0 volts when we're talking about lithium plating. There's also the side reaction current density, which is locally dependent on the electrolyte concentration. So the side reaction is semi-irreversible. It's not completely irreversible like a Toffel equation, because we do have an anodic rate term. We do have that term in the equation, but we can't allow overall positive side reaction flux coming out of this equation. We compute the we stick this equation here into a pseudo 2D Newman style model. Just add this one equation, and that allows us to compute all of the concentrations and potentials and the normal intercalation flux plus the side reaction flux. The side reaction happens only in spatial locations where the overpotential is less than 0. If you look at this and you compare these two things, that's what you're going to find, is when overpotential is less than 0, we have the side reaction occurring. And that's enforced by this min function, which sets the side reaction flux to 0 anywhere that the eta is positive, but to the value computed by the Butler-Volmer equation when the side reaction overpotential is negative. So if we plot this overpotential of the side reaction versus space at some point in time, this is just a cartoon, it's not an accurate plot, but this is the current collector, this is L neg, the separator boundary, and it's saying that the overpotential is positive for this whole area, region, but at some x location x0, the overpotential goes negative and is negative down to L neg. Well, the equations say that in this interval here, between x0 and L neg, I will have lithium plating. I will not have lithium plating in this region because the side reaction overpotential is positive in that area. And this example, this illustration, while it's not a computed plot, does at least give the idea that it's possible for a cell to be quite far away from 100% state of charge. So you can imagine that the rest over potential might be like this. But current traveling through the cell, charging the cell, is forcing the overpotential to get smaller and smaller and smaller near the separator, and finally lithium plating happens near the separator. So based on this kind of equilibrium overpotential, we might imagine that the state of charge of the cell might still be quite far away from 100%, but I still have lithium plating if I have a large enough charge current pulse applied to the terminals of this cell. So the state of charge is only one variable of importance. The local overpotential is what determines whether plating occurs or not. So when we make a reduced order model, our first goal is to solve for the side reaction overpotential. And once we've solved for that, we can incorporate it into an incremental set of equations for film resistance and capacity loss. Basically the same thing that we did when we looked at the SEI model of Ramadas, except we will solve for JS in a different way because the equations leading up to it are different. We're going to assume that the JS is constant over some small time interval delta t, and again we'll denote it as JS comma k for the kth interval. Again, we convert the continuous time film growth equations into a discrete time set of film growth thickness equations. Same as before. Possibly we'll have different molecular weights and densities of the products formed by the lithium plating versus the SEI growth, but it's the same basic equation. And similarly, we have the same basic equation for film resistance, and we have the same basic equation for capacity loss as we had before. So the main difference in how this model works compared to the SEI model is how we compute a reduced order approximation of JS. And we're not going to go over all of the methodology in the paper. You're, of course, welcome to download the paper and read it and see what we did. It turns out to be more complicated than the SEI because of the geometries involved and how that all works out. But we did come up with a set of algebraic reduced order equations that don't require the full 1D model of the cell in order to implement them. We simulated it and we got some results, and that's what I'm going to share in the next section.